Hi, Alicia and Rachel.
Hi, girls. Hope you're having fun. We sure are. We're going to be finding work with line integrals. It can't get much more fun than that, let me tell you. Look at our learning target. I can find work with line integrals. What you learned earlier in this chapter, not this chapter, but at the start of the year, coming full circle with 12.3, we found that work had a vector formula to it. It was a dot product. To calculate work, this is going right at the start of the school year. It was a force vector dot producted with a displacement vector, PQ. And what we're going to do is revisit that idea, but now we're going to be dealing with a vector field. That's how we started chapter 16 off. Remember, a vector field was such that at any point, either on a two-dimensional plane or in 3 space, for any point x, y, z, we could plug that into a function, a vector function, and get a vector associated with that point. So we've got a continuous vector field, but we're going to compute work done by this force moving a particle along a smooth curve C. So very, very important to point out that we do have a force field or a vector field in play, but we're traveling along a curve labeled C, and we'd like to measure the work done moving a particle along this curve. So you obviously are thinking, well, we need to deal with the displacement vector. We need to have a dot product. So we have a force vector that's going to be found from that F function that we have. But here's what we're going to do. Divide that curve into equal subarcs. So we're looking at arc length, but we're going to break it into little equal pieces. And so at any point on that curve, P sub I, we could find a tangent vector, and in fact, a unit tangent vector. Because again, we need to find some displacement. So remember, a unit tangent vector has a length of 1, of course, and as we're looking at any point, you can see that that unit tangent vector is represented right here. We're going to multiply that by delta S. Now, delta S might be very, very, very small. And what you're going to have at the end of the day, though, is a vector. It's going to really indicate the displacement that that point is moving on a very tiny portion of that curve for just a delta S on that arc length. So what you can do is taking these two things together, the tangent vector multiplied by that ds, is a displacement vector. Have your dot product with that f function right there. That's going to be what we have for work. So we're, of course, evaluating this along a curve, and that's the big difference that we're dealing with in this chapter. We're working on a curve, and we're integrating along that curve. Now, as you notice, the ds, what we talked about previously, we said it was the square root of dx dt squared plus dy dt squared plus dz dt squared, but that's really the length of r prime. If r is the position vector, r prime, as we take our derivatives of dx dt, dy dt, and dz dt, find that length, apply the Pythagorean theorem, that can be very, very helpful as we look at this integral in a different way. So, first of all, remember that a unit tangent vector, just having some review from chapter 13, it was r prime of t divided by the length of r prime of t. That's how we always guaranteed that our length was 1. So what's happening is, guys, we've got our force function right here, if I'm plugging in my r of t, and of course we have a parametrization of that curve right here, just plug that in that regard. Take our unit tangent and write it as r prime of t all over the length of r prime of t, but then take our ds, which is right here, and say, wow, instead of writing ds, we could write the length of r prime of t dt. What you can see is, even though we do have a dot product, these are constants right here, or they would effectively be like a length that would be worked out. So you could even cancel those out. And what we're left with is this very, very simple formula to find work. It's going to be that force function in its parametric form, dot producted to r prime of t dt. And of course, our t parameter is going to span between a and b. So, just one little thing to point out to you. As you see this, a lot of times in our textbook, you might see an abbreviation for it. And it would be the line integral of f dotted to just a dr. And that can look rather strange to kids at first. And you can think, how in the world could that actually be equivalent? Well, look at what we have. Dr dt is r prime of t. But if I were to solve for dr, I could just multiply both sides by dt. And, all of a sudden you could see that dr right here is in fact what we have for our r prime dt. So that's, what the author might write sometimes. But in this box, definitely we have the way that we can find work. The way that you're probably going to be going about this, undoubtedly, is there in the middle. And we're jumping to that very, very soon. It's very important to remember, too, that when you see that f of r of t right here, all it's saying is it's that f vector function plugging in the parametric form for our curve, where r has a parametric form to it. So x is a function of t, y is a function of t, z is a function of t. We're going to substitute all of those into our force vector function. So let's actually get started and do some work together right now. And it says, find the work done by this force field where we have F is equal to x squared vector I minus xy vector j. And, first of all, I do want to just point this out to you. What you really want to be able to do immediately is look at your R formula, where you're saying, look, this is a vector-formed curve, but let's write this out parametrically. Everywhere where we see an x of t is really representing what? Cosine of t, right? That's your x component. Y of t would be sine of t. Okay, so that's very, very important right there. When you look at f of r of t, the way it was written in the notes, what it's really saying is come back here to your force function, but use those parametric forms and rewrite f really just in terms of t. So when I see x squared I, I'm going to write cosine of t squared I. And then I'm going to say x times y. Well, I'll have cosine of t, and my y will be the sine of t, and then we'll have vector j. So that really is my force vector equation. my force vector function. The benefit, of course, is we're looking at this now as a function of t. And, r is right over here. Help me out. What's r prime of t going to get you? R prime of t, take your derivative. What's the derivative of cosine of t? We get negative sine of t. And the derivative of sine is cosine. So wow, look at that. Believe it or not, we pretty much are ready to calculate our work. You see, what we saw was work was this line integral where we could definitely change from a line integral. As you can see right here, the benefit is in the middle, I have this as a function of t, really. So we could have f of r of t dotted with r prime of t dt, and my t boundaries are going to go between 0 and pi over 2. So, tell you what, we're going to be integrating between 0 and pi over 2, but this vector is really cosine squared t, and then I've got negative cosine of t, sine of t. But I'm going to have the dot product with r prime. Now r prime, I can write it out in this bracket notation. We could say that's negative sine of t, cosine of t, rather than write it out in terms of i's and j's. Okay? So guess what you have to do? You've got to work out your dot product. And I hope you remember that. The dot product was actually a nice, easy, direct thing to calculate. You've got to multiply your first items. You'd get negative sine of t times cosine squared of t. Just multiply the first entries plus, now you multiply your second entries. And you could say, well, that's going to be a negative again. And I'll have a sine of t. Then I'll have cosine squared of t. I've got another one of those. Wow. Well, at this point, guys, you're not really looking at a line integral anymore. You're ultimately just going back to last year, and you're able to say, well, these are like terms. This is a negative 2 sine of t cosine squared of t. And it's at this point where, of course, we could go ahead and work this thing out. Now I'm going to really just continue the work up here. So I'll pull my negative 2 out. And, of course, we could evaluate this via a calculator, but you know what? It's good to keep our skills up in calc. How would we work this out by hand? What u substitution? What do you think we could let u equal? Maybe cosine of t, perhaps. Excellent. So du would be negative sine of t dt. And you could say dt would be your du all over negative sine of t. And, our bounds are going to change. I'm plugging in a 0. What's the cosine of 0? That would be a 1. And what about plugging in pi over 2? What's the cosine of pi over 2? That would be 0. And, I've got my sine of t over here. Here's my u squared. And dt would be a du all over a negative sine of t. Hopefully you can see that these negatives are going to cancel out, of course. And so will the sine of t's. Right? These are gone, and that's gone. So, wow, at this point, we definitely can, finish working this thing out. Don't worry that your bounds appear to be upside down. That's okay. Antiderivative of u squared is u cubed all over 3. And then we'll plug in our 0 and our 1. And we still have a 2 out in front, don't we? So I've got my 2/3 here. I can just pull those out. I'd have 0 cubed minus 1 cubed. Hopefully you can see that the work done is actually going to be negative 2/3